The black hole at the center of the Milky Way weighs as much as 4 million suns. Sagittarius. A star, as astronomers call it, swallows everything that gets too close. Light, matter, time. Everything vanishes behind an invisible boundary we call the event horizon. But here is what truly makes one wonder. The radius of this horizon, calculated using the formula of the German physicist Karl Schwarzschild more than a century ago, mysteriously coincides with the dimensions of the observable universe. A coincidence or a hint? Imagine that everything we know, galaxies, stars, planets, we ourselves, is actually located not in infinite space, but inside a giant black hole. That the sky above us is not just the emptiness between stars, but curved space-time behind the event horizon. That the edge of the observable world is not a technical limit, but a fundamental boundary of reality. It sounds crazy. Back in 1972, theoretical physicist Pathria and mathematician Irving Good independently proposed this hypothesis. They noticed something strange. Our universe behaves exactly as matter inside a black hole should behave. The expansion of space that we observe and call the consequence of the Big Bang might in fact be the fall of matter toward the event horizon. And what we take for the boundary of the visible world, where galaxies scatter at the speed of light, is that very horizon from which there is no escape. But the most terrifying thing about this theory is not that we are trapped. The most terrifying thing is that we might not even suspect it, because the laws of physics inside a black hole work exactly the same way as outside. Time flows, space expands, stars are born and die. Everything looks normal until you start looking closely at the details. In 2010, Polish physicist Poplawski developed this idea further. He showed mathematically how matter falling into a black hole in some parent universe could not collapse into a singularity, but bounce back. Bounce back like a compressed spring and begin to expand, creating an entire new universe, ours, inside the hole. And if his calculations are correct, then every black hole we observe in space is a door to another world. And we ourselves live in one of those doors. Recently, the James Webb Space Telescope discovered something strange. 2/3 of ancient galaxies rotate in the same direction. This should not be. The rotation of galaxies should be random, but the data shows a clear pattern. And the only reasonable explanation that occurs to physicists is that the universe was born rotating, and it could only rotate if it appeared inside a rotating black hole, inheriting its angular momentum. We stand on the threshold of a revolution in our understanding of reality. Perhaps everything we considered space has boundaries we do not even suspect. Perhaps beyond our world exists another universe, much larger and stranger. And perhaps our Big Bang is just the moment when the matter of another world passed through a quantum bounce and created us. Today we will dive into one of the most radical and simultaneously mathematically grounded theories of modern physics. We will analyze why the dimensions of our universe suspiciously coincide with the dimensions of a black hole. We will learn how the expansion of space can be a quantum bounce and try to understand the consequences of this idea for our representation of reality. If this theory turns out to be true, everything will change. Our representation of the beginning of the universe, its fate, our place in the cosmos, everything will have to be rewritten because we are not at the center of events. We are inside. But before pressing the subscription button and diving into this rabbit hole with me, ask yourself, are you ready to find out that your reality is someone else's black hole? If yes, then welcome. Now we will set off to where there is no return. By the way, if you appreciate such deep dives into the mysteries of space, be sure to subscribe to the channel and give it a like. Ahead of us lie even more exciting topics, from quantum paradoxes to the mysteries of dark matter. Do not miss it. And now let's figure out how a formula written in the trenches of the First World War led us to such a revolutionary idea. 1916. The First World War is turning Europe into a mess of trenches and gas attacks. On the Eastern Front serves 43-year-old German astronomer Karl Schwarzschild. He is not on the front line. He is too valuable a scientist to risk in bayonet attacks. He was sent to the artillery, where he calculates the trajectories of shells. But even here, in the mud and cold of war, his brain does not stop working on truly important things. A few months ago, Albert Einstein published his general theory of relativity, a revolution in the understanding of gravity. Instead of Newtonian attraction between masses, Einstein proposed thinking of gravity as the curvature of space-time itself. Massive objects bend the fabric of reality, and other bodies move along these bends like marbles rolling along a dent on a rubber sheet. The theory is elegant, beautiful, and incredibly complex mathematically. Einstein himself believed that exact solutions to his equations did not exist. They were too tangled. Schwarzschild read Einstein's article in a trench between calculations of artillery salvos and did what seemed impossible. He found an exact solution to the gravitational field equations for the simplest case, a spherically symmetric, non-rotating mass in empty space. He wrote a letter to Einstein with detailed calculations. Einstein was shocked. What he considered unsolvable was solved in a few weeks by an unknown astronomer right at the front. But the strangest thing in Schwarzschild's solution was not that it existed, but that it predicted something completely insane. It followed from the formulas that if any mass is compressed to a certain radius, gravity will become so strong that even light cannot escape. An area of space-time will arise from which there is no exit. The boundary of this area, an invisible sphere of a certain radius, which would later be called the Schwarzschild radius, would become the point of no return. Cross it, and there is no way back. For the Sun, this radius would be about 3 kilometers. Imagine that you take the entire mass of our star, almost 2 quadrillion kilograms of incandescent plasma, and compress it to the size of a small city. At that moment, space-time around it will curve so much that it will collapse into itself. For the Earth, the critical radius would be less than 1 centimeter. All mountains, oceans, continents, compressed into a ball the size of a cherry. Schwarzschild sent his solution to Einstein in January 1916. 3 months later, he died of a rare skin disease he contracted at the front. He was 42 years old. He did not live to the moment when physicists would understand that his formula describes not just a mathematical abstraction, but real objects, black holes. Moreover, he could not have guessed that his solution would one day overturn our representation not of some distant stars, but of the universe itself. Because a strangeness lurks in Schwarzschild's formula. The radius of the critical sphere depends only on mass. The larger the mass, the larger the radius, linearly. Double the mass, double the radius, and there are no limits on the size of the mass. Theoretically, one could take the mass of a galaxy, the mass of a cluster of galaxies, the mass of the entire observable universe, and calculate the Schwarzschild radius for it. Someone did just that and discovered something shocking. The Schwarzschild radius for the mass of the observable universe turned out to be approximately equal to the size of the observable universe itself. Not 2 times smaller, not 10, approximately equal. As if someone specially selected the mass and size so that we would be right on the edge, on the event horizon of a giant black hole. For decades, physicists ignored this coincidence. They said it was just a game of numbers, a coincidence of orders of magnitude, nothing special. But the coincidence is too precise to be accidental and too fundamental to be simply brushed aside. And then Pathria and Good appeared and said, "What if it is not a coincidence? What if our universe is indeed inside a black hole? What if everything we observe, expansion, acceleration, the cosmological horizon, is exactly how it should look from the inside?" Schwarzschild opened the door to the world of black holes without knowing it himself. He thought he was describing the behavior of massive stars, but he described, perhaps, the structure of all reality. The irony is that his formula is simple: 2gm divided by c squared. That is all. But these few symbols may contain the answer to the question of where we actually are. When Schwarzschild first wrote down his solution, he could not imagine that he was describing something real. In 1916, black holes were pure fiction, a mathematical curiosity that many thought would never be encountered in nature. Even Einstein for a long time doubted that such objects could exist physically. It seemed absurd that matter could collapse into a point of infinite density surrounded by an invisible boundary of no return. But mathematics does not lie, and Schwarzschild's solution was flawless. It described space-time around a point mass, a mass compressed so much that its own radius is zero. Around this singularity, space curves according to a certain law. And at the distance we now call the Schwarzschild radius, something strange happens. The geometry turns inside out. Outside the Schwarzschild radius, time flows like time, and space remains space. You can move forward, backward, left, right, up, down, and time only flows forward. But as soon as you cross this invisible boundary, the coordinates swap places. The radial direction, movement toward the center, becomes the direction of time, and time turns into a spatial coordinate. It sounds crazy, but it is a direct consequence of mathematics. What does this mean in practice? It means that inside the Schwarzschild radius, movement toward the center is inevitable, just as inevitable as movement into the future is for us. You cannot stop. You cannot turn around. You can only fall toward the singularity, and this fall is your time. When you stop falling, time will also stop. But you cannot stop, because that would violate causality. Therefore, you fall until you reach the center. For an external observer, everything looks different. If you watch someone falling into a black hole, you will see that person slow down. The closer to the event horizon, the slower the image moves. Time for the falling person, from your point of view, stretches, and in the limit, when he reaches the horizon, it will stop completely. You will see him frozen at the boundary for centuries, for millennia, forever. The light from him will become increasingly red until it disappears completely. But for the falling person himself, everything happens quickly. He crosses the horizon in a finite time, seconds, minutes, hours, depending on the size of the black hole. He will feel nothing special during the crossing, no walls, no barriers. Just at some point, he realizes there is no way back, and only the singularity lies ahead. This is a black hole according to Schwarzschild, an area of space-time with a one-way membrane. You can enter, you cannot leave, and this membrane, the event horizon, is determined by a radius that depends only on the mass of the object inside. But what will happen if we try to apply the same logic to the universe? If we take all the mass we see around us, galaxies, stars, gas, dark matter, and calculate the Schwarzschild radius for it, it turns out to be about 10 billion light-years. And what is the size of the observable universe? Also about 10 billion light-years. To be more precise, the Hubble radius, which determines the boundary of the observable world, almost coincides with this number. This may be a coincidence or a hint, because if our universe is indeed inside a black hole, then we should be right on its event horizon or inside it. And everything we observe, the red shift of galaxies, the expansion of space, the cosmological horizon, is exactly what should be observed from the inside. Imagine that you are an observer inside a giant black hole. You do not know that you are inside because the size of the hole is so enormous that locally space looks flat. But you notice something strange. All distant objects are running away from you. The further they are, the faster they move away, and at a certain distance they reach the speed of light and disappear behind the horizon. Sounds familiar? This is exactly what we see in our universe. Hubble's law, which says that the speed of receding galaxies is proportional to the distance to them, and the cosmological horizon, beyond which galaxies move away faster than light and become unobservable. We interpret this as the expansion of space after the Big Bang. But what if it is just the effect of being inside a black hole? Schwarzschild could not know where his solution would lead. He thought about stars and planets, about the trajectories of light around the sun, about the precession of the orbit of Mercury. He did not think about cosmology, but his formula turned out to be universal. It works for any mass, for any scale, and when you apply it to the largest scales, to the entire observable universe, mathematics gives a striking result. The radii coincide. Now the question, is it accidental, or do we really live in a black hole, just one large enough not to notice it locally? And if so, where is this hole located? In what universe? And does someone exist outside for whom our entire 14 billion year history is just a moment? By itself, the Schwarzschild radius is just a number, a characteristic stemming from the mass of the object. But when you start comparing these numbers for different objects in the universe, a strange pattern appears. For ordinary bodies, planets, stars, even neutron stars, the Schwarzschild radius is negligibly small compared to their real size. The Earth, for example, has a radius of about 6,500 kilometers, and its Schwarzschild radius is less than 1 centimeter. The Sun is about 700,000 kilometers in radius, and the critical radius is only 3 kilometers. This means that ordinary bodies are far from the edge beyond which they would collapse into a black hole. They need to be compressed millions or billions of times to reach their Schwarzschild radius. And nature does not provide such compression tools for most objects. Even stars, when they die, either turn into white dwarfs or explode as supernovae and leave a neutron star. And only the most massive of them, those that weigh more than 3 solar masses in the remainder, collapse into a black hole. But there is an exception. If you take a large enough mass distributed fairly evenly in space, its own gravity will not compress it into a point. Instead, it will expand or contract depending on its density. And if this density turns out to be close to critical, and the mass is very large, the Schwarzschild radius of such a system may coincide with its real size. This is exactly what happens with the universe. If you take the entire mass of the observable universe, about 10 to the power of 53 kilograms by estimates, and calculate the Schwarzschild radius for it, you get about 10 billion light-years. And the radius of the observable universe, more precisely the Hubble radius, which determines the boundary of the region from which light reaches us, is also about 10 billion light-years. Considering expansion, the current size of the observable region is even larger, but the order of magnitude is the same. Coincidence? Physicists thought so for a long time. They said it was just a numerical accident, the result of us living in a certain era of cosmic evolution when the density of the universe is just such that these two numbers are close. In billions of years, when the universe expands even more and the density drops, the coincidence will disappear. So nothing special. But there is a problem with this explanation. First, the coincidence is too precise. Not by an order of magnitude, but practically 1-to-1. Second, it has been maintained throughout the billions of years of the history of the universe, which is strange if it is just an accident. And third, there is a theoretical reason why this may not be a coincidence, but a fundamental property of our reality. Because if the observable universe is inside a black hole, its size, by definition, must be close to the Schwarzschild radius of that hole. The event horizon of a black hole is a sphere of the Schwarzschild radius. And if we are inside, then the maximum region we can observe is limited precisely by this horizon. Not because there is nothing beyond it, but because information does not reach us from there. Light cannot go outside the event horizon. Similarly, it cannot come to us from the inside if we are on this horizon. Moreover, if the universe expands from within a black hole, this expansion will look exactly like the receding of galaxies that we observe, because the matter inside the black hole falls toward the center. But in curved space-time, this fall can look like the expansion of three-dimensional space. It sounds paradoxical, but the mathematics of general relativity allows such things. Falling in the radial direction of four-dimensional space-time can manifest as expansion in the three-dimensional space that we perceive. And this is where the most interesting part begins. If our universe is indeed inside a black hole, then the event horizon that we call the cosmological horizon is not just a limit of observability due to the finite speed of light. It is a real event horizon of a black hole, a boundary beyond which nothing can go, including us. We are used to thinking that the cosmological horizon is just a technical limitation. They say the universe expands, and at some distance from us, galaxies move away faster than the speed of light. Therefore, we do not see them. But beyond this horizon, there is still the universe, just inaccessible for observation. We cannot get there because of the finite speed of light and accelerating expansion, but the continuation of the cosmos exists there. However, the mathematics of black holes suggests a radically different interpretation. What if the cosmological horizon is not just a visibility boundary, but an event horizon in the full sense? Then beyond it is not a continuation of our space-time, but a fundamentally different region, the external universe containing the black hole with us inside. Physicists have checked this coincidence of radii many times, tried to find an explanation within the framework of standard cosmology, talked about dark energy, about the cosmological constant, about the dynamics of expansion. But none of these models explain why the coincidence is so precise and why it exists at all. The only explanation that makes this coincidence natural and not accidental is the black hole hypothesis. If we are inside, the radii must coincide. This is not a coincidence, but a geometric consequence. The Schwarzschild radius determines the event horizon, and the event horizon determines the boundary of the observed region from the inside. Therefore, these two numbers are one and the same number seen from different sides. But if this is so, then why do we not notice that we are in a black hole? Where is the singularity? Where is the monstrous gravity tearing everything apart? Where is the distortion of time and space that make black holes so terrifying? The answer is simple. A black hole from the outside and from the inside are two different worlds. From the outside, it looks like a region of infinite density surrounded by an invisible boundary. From the inside, it looks like expanding space filled with galaxies. Both are correct descriptions of the same geometry, just from different sides of the event horizon. So the coincidence of radii is not just a funny fact. It is a hint. Perhaps the most important hint about the nature of our universe we have ever received. And we are only beginning to understand what it means. Now let's dive deeper and find out who first dared to utter this crazy idea aloud. 1972. Physics is at a crossroads. Einstein's general theory of relativity has been accepted for half a century. Black holes have turned from a theoretical curiosity into objects that astronomers are seriously looking for in space. And cosmology is undergoing a revolution. Cosmic microwave background radiation has been discovered, proving that the universe was born in the Big Bang. It would seem that everything fits, but it is at this moment that two people, independently of each other in different parts of the world, express the same heresy. The first is Raj Pathria, an Indian theoretical physicist working at the University of Delhi. The second is Irving Good, a British mathematician, a participant in the project to decrypt Enigma during World War II, a colleague of Alan Turing. Both study cosmology, both try to understand why the universe is arranged exactly this way and not otherwise, and both come to the same shocking conclusion. The observable universe may be inside a black hole. Pathria publishes his work first. He considers Schwarzschild's solution and asks a simple question. What will a person inside a black hole observe? Not someone falling into it, but someone already there, in a stable region inside the event horizon. The mathematics of general relativity allows for such regions. If a black hole is large enough, there may be space inside it where matter is not torn apart by tidal forces, where time flows relatively normally, where it is possible to exist. And Pathria discovers something strange. Such an observer will see expanding space around him. For him, distant objects will move away, and faster the further they are. He will see a red shift in the spectra of distant galaxies. He will record a cosmological horizon, a boundary beyond which objects move away faster than light. All these are direct consequences of the geometry of space-time inside a black hole. Sounds familiar? This is exactly what we observe in our universe. Hubble's law, expansion, redshift, cosmological horizon, everything is in place. We interpret this as a consequence of the Big Bang, the initial expansion from a singularity 14 billion years ago. But Pathria shows that exactly the same picture will be seen by an observer inside a large black hole. Mathematically, these two situations are indistinguishable. Moreover, Pathria draws attention to the coincidence of radii. The Schwarzschild radius for the mass of the observable universe is approximately equal to the Hubble radius. This is not a trifle. It is a fundamental equality. And if this is not a coincidence but a pattern, then the logical explanation is one. The observable universe is the interior of a black hole located in some larger parent universe. Good comes to the same conclusion independently, using a slightly different approach. He considers not the geometry of space-time, but the thermodynamics of black holes. The entropy of a black hole is proportional to the area of its event horizon. The larger the hole, the more information it can contain. Good asks the question, what if inside a black hole this information is organized in the form of an entire universe with stars, galaxies, and planets? He shows that this does not contradict the laws of physics. Moreover, such a structure of a universe within black holes, which in turn contain black holes with their own universes, can be infinitely nested, a matryoshka of realities. And our universe is just one of the levels of this hierarchy. Both works came out almost simultaneously, in '72, and both were almost completely ignored by the scientific community. Physicists treated them as mathematical speculations, interesting but having no relation to reality. They argued that yes, mathematics allows such a possibility, but there are no observational data confirming it, which means it is just a game of the mind. The problem is that verifying such a hypothesis is incredibly difficult. If we are inside a black hole, we cannot look outside to make sure. The event horizon is an absolute barrier. No information passes through it in the opposite direction. We are trapped inside if the hypothesis is correct, and we have no way to contact the external universe, send a signal, or receive confirmation. But Pathria and Good suggested indirect ways of verification. If the universe is inside a black hole, it must have certain properties that can be observed from within. For example, it must be rotating, because most black holes rotate, having inherited the angular momentum of a collapsing star. And if the universe rotates, this must manifest in the distribution of galaxies, in their orientation, and in the large-scale structure of the cosmos. In the '70s, astronomers did not have the instruments for such measurements. Telescopes were not powerful enough, galaxy catalogs were not complete enough, so the hypothesis remained just a hypothesis, an entertaining idea that was occasionally recalled at conferences but not seriously considered. But the idea did not die. It waited for new data, new telescopes, new physicists who would dare to look at it without prejudice. And they appeared almost 40 years later. What if Pathria and Good were right? What if they saw what others did not want to see? Not because it is impossible, but because it overturns our entire representation of the cosmos. What if the Big Bang is not the beginning of everything, but simply the moment when the matter of a parent universe fell into a black hole and created us? Before the Big Bang, there was another time, another space, another reality. And we are a byproduct of gravitational collapse in a world we do not even suspect. And the most terrifying thing, if this is true, is that we will never be able to get out, because the event horizon of a black hole is a one-way road. There is an entrance ticket, but no exit. We can build ships, fly to the stars, explore galaxies, but we will forever remain within the boundaries of this region of space-time, because the laws of physics do not give a chance to cross the event horizon in the opposite direction. This is a fundamental prohibition built into the very geometry of reality. But before we resign ourselves to such a fate, let's find out what happened next. Because the Pathria good hypothesis did not disappear, it evolved. And in 2010, a person appeared who gave it mathematical rigor and concrete predictions. A person who showed how black holes can give birth to entire universes and how our universe can be one of them. Poplawski, a Polish theoretical physicist working at the University of New Haven in the United States. In 2010, he published a series of articles that turned the Pathria good hypothesis upside down, or more precisely, placed it on a mathematically firm foundation. Poplawski does not just say that a universe can be inside a black hole. He shows exactly how this happens, what physical processes are behind it, and what can be expected to be observed if it is true. His approach is based on an extension of the general theory of relativity, the Einstein-Cartan theory. In classical general relativity, space-time curves under the influence of mass and energy, but it does not twist. In Einstein-Cartan theory, the torsion of space-time caused by the rotation of matter is added, and this torsion changes everything. In ordinary general relativity, when a massive star collapses into a black hole, all its matter falls to the center and collapses into a singularity, a point of infinite density where the laws of physics stop working. A singularity is a mathematical and physical problem. It is a place where the theory breaks down, predicting infinities that should not exist in nature. But in Einstein-Cartan theory, everything is different. When matter is compressed to incredible densities, the torsion of space-time creates a repulsive force. This is not an ordinary repulsion, not electromagnetism, and not nuclear forces. This is a quantum gravitational repulsion that manifests only at extreme densities close to the Planck density, the highest density that has any physical meaning at all. When matter reaches this density, it cannot be compressed further. Instead of collapsing into a singularity, it bounces back like a spring compressed to the limit, bounces back with enormous force, beginning to expand. And this expansion is the Big Bang. Not a beginning from nothing, but a bounce from a state of maximum compression. But here is what is truly striking in Poplawski's model. This bounce occurs inside a black hole. Matter collapses below the event horizon, is compressed to the Planck density, bounces back, and begins to expand. But it cannot go back out through the event horizon. The horizon is a one-way membrane, so the expansion occurs inside, creating a new space-time, a new universe enclosed within the boundaries of the event horizon. For an external observer, this universe is invisible. He sees only a black hole, a massive object with an event horizon of a certain radius. He does not know that an entire history is unfolding inside. Galaxies, stars, planets, possibly life are born. All this is hidden behind the horizon. And for the inhabitants of the inner universe, the external world is equally inaccessible. They see an expanding cosmos, distant galaxies, a cosmological horizon. They do not suspect that their world is the interior of a black hole in another universe. Poplawski goes further. He shows that such a structure, a universe inside a black hole, can be self-reproducing, because in the new universe created inside a black hole, stars also appear. Stars also collapse into black holes, and inside these black holes, new universes are born and so on to infinity. The result is a cosmic matryoshka, an infinite hierarchy of universes nested into each other through black holes. Each universe gives birth to many black holes, inside which new universes are born, and it itself is possibly inside a black hole of a parent universe, which in turn is inside its parent, and so on. This is not just philosophical speculation. Poplawski gives concrete mathematical equations describing this process. He calculates what the internal geometry of such universes should look like, what observational effects they should produce, what traces of their origin they should carry. And one of the key predictions is rotation. If a universe was born inside a black hole, it must inherit the angular momentum of that hole. Most black holes rotate. This is a consequence of the fact that collapsing stars rotate, and angular momentum is conserved during collapse. This means that a universe inside a rotating black hole must also rotate. How will this manifest? In the large-scale structure of the cosmos, galaxies should not be distributed randomly. Their rotation, their orientation, their movements must bear the imprint of the overall rotation of the entire universe. There should be a preferred axis of rotation around which the entire cosmic structure is organized, something like an axis of the world, an invisible line determining the direction of rotation of our reality. In 2010, such data did not exist. Astronomers did not see any signs of large-scale rotation of the universe. Moreover, standard cosmology claimed that the universe is isotropic, the same in all directions. There is no distinguished axis, no preferred direction. This is one of the main postulates of the cosmological model. Therefore, Poplawski's theory remained controversial, mathematically beautiful, conceptually intriguing, but not confirmed by observations. Many physicists treated it skeptically, saying it was too speculative, too far from verifiable predictions. But Poplawski did not give up. He continued to develop the theory, refine the calculations, and looked for new ways to verify it. And most importantly, he waited. He waited for technology to reach the level allowing for the necessary observations. He waited for new telescopes, new galaxy catalogs, new methods of data analysis, and he got his wish. In 2021, the James Webb Space Telescope was launched into orbit. The most powerful observation instrument ever created by humanity. Capable of looking into the most distant corners of the universe, seeing galaxies that existed only a few 100 million years after the Big Bang, capable of measuring their shapes, their rotations, their distributions with unprecedented precision. And in 2025, Webb brought the first results. Results that made physicists remember Poplawski's forgotten theory, because the data showed something strange, something that should not have been there according to standard cosmology, but that perfectly fits into the model of a universe born inside a rotating black hole. Poplawski's theory explains not only the origin of the universe, but also its fate. If we are inside a black hole, sooner or later we will reach its center, not in a spatial sense. The center of a black hole is not a point in space, but a moment in time, a singularity in the future. But in Einstein-Cartan theory, there is no singularity. There is a moment of maximum compression, after which a new bounce, a new Big Bang, a new cycle can occur. So perhaps our universe is cyclic, expanding to a certain point, then contracting back, reaching the Planck density, bouncing back, and starting all over again. An eternal cycle of deaths and rebirths enclosed inside a black hole. And each cycle can be slightly different, with slightly different constants, slightly different laws of physics, a slightly different history, but that is already philosophy. For now, we have a concrete theory, concrete predictions, and finally, concrete data that can be compared with these predictions. And these data came from the James Webb Telescope. Let's see exactly what it discovered. The event horizon is one of the strangest concepts in physics. It is a boundary that can be crossed, but one cannot return. It is not a wall, not a barrier, not a physical object. It is a geometric property of space-time. An invisible surface in 4 dimensions that divides reality into 2 regions, the one from which you can escape and the one from which you cannot. For a black hole, the event horizon is a sphere of the Schwarzschild radius. Outside this sphere, gravity is strong but not omnipotent. If you move fast enough, you can leave the vicinity of the black hole and fly away. But as soon as you cross the horizon, all directions outward disappear. Only one direction remains, toward the center. And moving in this direction is as inevitable as moving into the future. But the universe also has an event horizon, the cosmological horizon. This is the boundary of the observable world, beyond which galaxies move away from us faster than the speed of light. We cannot see what is happening there because light from there will never reach us. The expansion of space carries it away faster than it can approach. It would seem that these are 2 different phenomena. The event horizon of a black hole is the boundary of no return for matter falling inside. The cosmological horizon is the visibility boundary for an observer in an expanding universe. The first is connected with gravity, the second with the expansion of space. Different causes, different consequences. But what if they are one and the same? What if the cosmological horizon is actually the event horizon of the black hole inside which we are located? Then everything matches. The dimensions match. The behavior matches. The mathematics matches. Not because it is a coincidence, but because it is one object viewed from different points of view. Imagine you are inside a huge black hole, so huge that locally space looks flat. Time flows normally, the laws of physics work as usual. But if this hole rotates, and most black holes rotate, its internal geometry will have a preferred direction, an axis of rotation. And this axis should manifest in the distribution of matter inside. Galaxies will not form randomly. Their rotation, their orientation will bear the imprint of the overall rotation of spacetime. There should be anisotropy, a violation of the isotropy predicted by standard cosmology. It is as if you were standing in an elevator that is freely falling. You do not feel gravity because you are falling together with the elevator. For you, everything is weightless, everything is floating. But if you look at other objects around you, they will move away from you, not because a force acts on them, but because you are all falling with different velocities in curved space. The dual nature of the event horizon manifests in how time behaves on it. For an external observer, time on the horizon stops. Everything approaching the horizon slows down and freezes. But for someone crossing the horizon, time flows normally. He does not notice anything special crossing this invisible boundary. The same is true with the cosmological horizon. For us, galaxies at the cosmological horizon should seem frozen. Their time has stopped. We see them as they were billions of years ago and will never see how they changed. But for them, everything is normal. They continue to exist, to evolve, but we will no longer see it. And this is where the key observation lies. If the cosmological horizon is the event horizon of a black hole, then beyond it, there should be not just another part of our universe. There should be a completely different world, a parent universe in which the black hole containing us is located, a world with possibly different laws of physics, a different number of dimensions, a different history. We cannot look there because the event horizon is absolute. But we can look for traces of this other world in how our own behaves. Because if we were born inside a black hole, we must carry the imprints of the conditions under which this hole was formed. Rotation, mass, charge. All this should manifest in the structure of our universe. And here the mathematics becomes even more beautiful. In general relativity, there is a theorem proven by Roy Kerr in '63. It says that any stationary black hole is completely described by just 3 parameters: mass, rotation, and electric charge. Nothing else. All other details about the matter that fell into the hole are erased. This is called the black holes have no hair principle. Only 3 numbers remain. Everything else disappears. If our universe is inside a black hole, it must carry information about these 3 parameters of the parent hole. Mass determines the size of the event horizon, and we see that the Hubble radius coincides with the Schwarzschild radius for the mass of the universe. This is the first parameter. Rotation should manifest in the large-scale structure. If the parent black hole rotates, our universe will inherit this angular momentum, which means there must be a preferred axis of rotation around which the cosmic structure is organized. This is the second parameter, and it is exactly what astronomers are looking for. The electric charge is most likely 0. Charged black holes are unstable. They are quickly neutralized by attracting oppositely charged particles from the surrounding space. Therefore, most astrophysical black holes are electrically neutral. And if our universe is inside such a hole, it must also be neutral on average, which we observe. So 2 parameters out of 3 are already verified and agree. Rotation remains, and it is exactly this that the James Webb Telescope data can confirm or refute. But before we move to these data, we need to understand one more aspect of the theory. How can the expansion of the universe be an illusion of falling into a black hole? Hubble's law is one of the pillars of modern cosmology. It says that all galaxies are moving away from us, and the speed of their removal is proportional to the distance to them. Distant galaxies run away faster than near ones, with a strictly linear dependence, twice as far, twice as fast. This observation, made by Edwin Hubble at the end of the 20s of the last century, became the basis of the Big Bang theory. The logic is simple. If galaxies are scattering, it means that earlier they were closer to each other, and even earlier very close. Following the evolution back in time, we come to a moment when all matter of the universe was compressed in one point. A singularity, the beginning of time, the Big Bang. But there is another interpretation of the same observations. What if galaxies are not scattering from us? What if they are falling together with us toward the event horizon of a giant black hole? Then the redshift effect we see in their spectra is not a consequence of space expansion, but a consequence of time curvature near the horizon. Imagine you are falling into a black hole together with many other objects. You are all moving toward the event horizon, but at different speeds. Someone is ahead, someone is behind. When you look at objects that are closer to the horizon, you see that their clocks run slower. Time for them flows differently due to gravitational time dilation. And a slow flow of time means that the light they emit shifts toward the red side of the spectrum. The closer an object is to the horizon, the stronger this effect. And when an object reaches the horizon itself, its time, from your point of view, stops completely. The redshift becomes infinite. The object disappears from visibility, not because it flew away, but because its time froze. Sounds familiar? This exactly describes what we see with the cosmological horizon. Galaxies on the cosmological horizon move away at the speed of light and disappear from visibility. We interpret this as space expansion, but it can also be interpreted as gravitational time dilation near the event horizon of a black hole. The mathematics of general relativity allows one to be reformulated through the other. The expansion of space is equivalent to a certain type of time curvature. The Friedmann-Robertson-Walker metric describing an expanding universe is mathematically connected to the Schwarzschild metric describing a black hole. These are not different solutions to Einstein's equations, but different representations of the same geometry. What does this mean practically? It means that everything we observe and call the expansion of the universe can be reinterpreted as the fall of matter toward the event horizon of a black hole. Redshift is gravitational time dilation. Acceleration of expansion is the approach to the horizon. The cosmological horizon is the event horizon of the black hole. But there is a subtlety. If we are falling toward the horizon, we must eventually reach it. And what then? Standard black hole theory says that after crossing the horizon, we will inevitably fall into a singularity. Matter will compress to infinite density, space-time will collapse, everything will end. But Einstein-Cartan theory, on which Poplawski's model is based, says otherwise. There is no singularity. When matter reaches the Planck density, quantum repulsion turns on and a bounce occurs. Not an end, but a transition to a new phase, a new cycle of expansion, a new Big Bang, but not from nothing, but from a state of maximum compression. And here a striking possibility arises. What if the process we call the expansion of the universe is exactly this bounce? What if the Big Bang occurred when the matter of a parent universe fell into a black hole, reached the Planck density, and bounced? Then expansion is not the movement of galaxies from a point of singularity, but the movement of matter from the moment of maximum compression toward the event horizon from the inside. We live in the bounce phase. Matter is expanding, but it is still inside the black hole, and sooner or later the expansion will slow down, stop, and be replaced by contraction. The universe will begin to collapse back. Galaxies that are now scattering will begin to draw closer. Space will shrink until it again reaches the Planck density. And then a new bounce, a new cycle. This idea of a cyclic universe is not new. It was discussed even by ancient philosophers. And in modern cosmology, it appears in different forms. But Poplawski's model gives it a concrete mechanism. Cycles occur inside a black hole. Each cycle is a phase from bounce to bounce. And these cycles can continue indefinitely, creating an eternal pulsation of matter inside the event horizon. But for now, this is a theory. Beautiful, mathematically grounded, but requiring observational confirmation. It is exactly such confirmations that recently came from the James Webb Telescope. Data that force one to seriously consider the possibility that the expansion of the universe is indeed an illusion hiding a much stranger reality. Let's see exactly what Webb discovered. 2021. The James Webb Space Telescope enters orbit. The most expensive and ambitious scientific instrument in human history. A mirror with a diameter of 6.5 meters, sensitivity in the infrared range, the ability to see galaxies whose light traveled to us for more than 13 billion years. The task is to look into the infancy of the universe, to understand how the first stars, the first galaxies, the first structures of the cosmos were formed. The observation program is enormous. Hundreds of objects, thousands of hours of exposure. But one of the projects is particularly interesting for our story. An advanced deep extragalactic survey. A team of astronomers studies ancient galaxies that existed only 300 million years after the Big Bang. The goal is to understand their shapes, their rotations, their distribution in space. And so in 2025, the first results are released. Data on 263 galaxies are clear enough to determine the direction of their rotation. Standard cosmology predicts that rotation should be random. Half of the galaxies spin clockwise, half counterclockwise. No pattern. The universe is isotropic. It has no preferred direction. But the data shows something completely different. 2/3 of the galaxies rotate in one direction, clockwise, if viewed from a certain point, and 1/3 in the other. This is not a coincidence. It is a statistically significant result. The probability that such a distribution arose by chance is less than 1%. Astronomers are in shock. This should not be. If the universe was born from a homogeneous singularity, from a point without preferred directions, how could it create an asymmetry in the rotation of galaxies? Where did this pattern come from? The variants of explanations begin to multiply. Could it be a measurement error? They check. No, the data are reliable. Could it be the effect of our movement in space? A Doppler shift that creates an illusion of preferred rotation. They calculate. No, the effect is too weak to explain the observation. Could it be a feature of that region of the universe that we observe? A local fluctuation. Possible, but unlikely. And then someone remembers Poplawski's theory. remembers that he predicted exactly such an effect. If the universe was born inside a rotating black hole, it must inherit the angular momentum, and this means that space itself must rotate, and the galaxies forming in this rotating space must predominantly rotate in one direction, the one set by the general rotation of the entire universe. Poplawski immediately responds to the publication, saying that this is exactly what he expected, that such asymmetry is natural if the universe is inside a black hole, that the preferred axis of rotation is the axis of rotation of the parent hole inherited by our world. But he goes further. He points out that if the hypothesis is true, asymmetry should manifest not only in the rotation of galaxies, it should be visible in other aspects of the large-scale structure. In the distribution of galaxy clusters, in the anisotropy of the cosmic microwave background, in the polarization of light from distant quasars. All this should bear the imprint of the rotation of the entire universe, and physicists begin to recheck old data from a new point of view. It turns out that hints of such asymmetry existed before. In the distribution of quasars, strange patterns were found that were dismissed as statistical fluctuations. In the cosmic microwave background, weak anisotropy was discovered, which was explained by the movement of our galaxy relative to the cosmic background. But if you look at all these data together with the hypothesis of a rotating universe in mind, they fit into a single picture. Not everyone is convinced. Many physicists remain skeptical. They say that one observation is not enough, that additional confirmations are needed, that alternative explanations are not yet excluded. And this is correct. Science requires skepticism, requires verification, and re-verification. But the fact remains. The telescope's data showed something that does not fit into standard cosmology. And the only theory that predicted such an effect in advance is the theory of a universe born inside a black hole. A coincidence or a hint? What does this mean? If true, it means that our universe has an axis, an invisible line in space around which everything rotates. Not locally, where each galaxy rotates around its center, but globally, the entire universe as a whole has an angular momentum directed along this axis. And this axis is inherited from the parent black hole in which we were born. Can we find this axis? Theoretically, yes. If one carefully analyzes the distribution of rotations of galaxies, clusters, and large-scale structures, one can calculate the direction around which this asymmetry is organized, and this will be the axis of rotation of our universe. An axis pointing to that point in the parent universe where the black hole containing us is located. But we will not be able to see anything in that direction because the event horizon is absolute. Beyond it is another world, inaccessible to us under any circumstances. All we can do is calculate the direction and know that there, on the other side of the horizon, something greater exists. A universe in which our universe is just the interior of one of the countless black holes. And while physicists argue about the interpretation of the Webb data, a more fundamental question arises before us. If we are indeed inside a black hole, where is the singularity? After all, classical theory says that in the center of every black hole there is a point of infinite density. So where is it in our universe and why do we not see it? The singularity is the strangest thing in general relativity. It is a place where mathematics breaks down, predicting infinities, infinite density, infinite curvature of space-time, infinite gravity. Physicists do not like infinities. When a theory gives an infinite result, it is usually a signal that the theory has stopped working, that something needs to be changed. In classical general relativity, a singularity is inevitable. Stephen Hawking and Roger Penrose proved a series of theorems that show if matter collapses below the event horizon of a black hole, it must reach a singularity. No forces can stop this fall, neither the pressure of matter, nor quantum effects, nor anything else. A singularity is the inevitable end of everything that falls into a black hole. but the Hawking-Penrose theorems are based on classical general relativity without taking quantum effects into account. And on the Planck scales, the smallest scales having physical meaning, quantum mechanics must become important, and it can change the picture. The Einstein-Cartan theory, which Poplawski uses, adds space-time torsion to general relativity. This torsion manifests only at extreme densities close to the Planck density, and it creates a repulsion, a quantum gravitational repulsion that stops the collapse before a singularity is formed. Matter is compressed, density grows, but when it reaches a critical value, the repulsion turns on. Matter cannot compress further. It bounces back like a spring that has reached its compression limit and begins to expand. This is called a quantum bounce, and it replaces the singularity with a finite state of maximum density. Not infinite density, but huge, yet finite. Roughly, Planck density is when a mass comparable to the mass of the Sun is concentrated in a volume the size of a proton. Monstrous, but not infinite. So in Poplawski's model, there is no singularity either in the center of a black hole or at the beginning of the universe. Instead of a singularity, there is a bounce. Instead of infinities, there are finite, though extreme, values. Mathematics remains correct, physics remains predictable. But then the question arises, where in our universe is this moment of bounce located? If we are inside a black hole and matter bounced from the Planck density, creating the expansion we observe, where and when did this happen? The answer is paradoxical. The bounce is not a place in space, it is a moment in time. For us, this moment is the Big Bang. The beginning of the expansion of the universe 14 billion years ago. We see it in the past as an event that happened everywhere simultaneously. But for an external observer located in the parent universe, it looks different. He sees matter falling into a black hole. It crosses the event horizon and disappears from his field of vision. From his point of view, time inside the black hole slows down and stops at the horizon. He will never see how the matter reaches the center, how the bounce occurs, how a new universe is born. For him, everything is frozen at the horizon forever. Two different perspectives, two different realities. From the inside, the Big Bang, expansion, the evolution of the universe. From the outside, a frozen collapse on the event horizon. Both are correct. Both describe the same situation, just from different sides of an impenetrable barrier. And what about the future singularity? If we are inside a black hole, should we not eventually fall into the center? Classical theory says, yes, after crossing the horizon, falling into the singularity is inevitable. But again, the Einstein-Cartan theory changes the picture. If the expansion of the universe is a phase of the bounce after the first compression, sooner or later it will slow down, gravity will take over, expansion will be replaced by contraction, and the universe will begin to collapse back. The galaxies that are now scattering will begin to draw closer, space will shrink, and when the density again reaches the Planck value, a new bounce will occur, a new Big Bang, a new cycle of expansion, and so on indefinitely. The universe pulsates inside a black hole, experiencing cycles of expansion and contraction, bounces from the Planck density, an eternal oscillation between two extremes. For us, each cycle looks like a separate universe, with its own beginning, its own evolution, and possibly its own end. But in fact, it is all the same matter, the same region of space-time, simply passing through repeating phases. So the singularity in Poplawski's model is not a place and not a final state. It is the limit of applicability of classical theory. Where general relativity predicts a singularity, quantum gravity predicts a bounce. And this bounce is what makes the universe inside a black hole alive, evolving, and eternal. We do not see a singularity because it does not exist. We see the consequences of the bounce, expanding space, forming galaxies, the evolution of the cosmos. And if the theory is correct, Someday in the distant future, in trillions of years, we will see the beginning of a new contraction. But this will not be the end, but the preparation for a new bounce, for a new cycle. And inside the black hole, life will continue. But there is another aspect of Poplawski's model that makes it even stranger and more exciting. He does not just suggest that we are inside a black hole. He suggests that a black hole is a tunnel, a wormhole connecting two universes. Wormholes are one of the most popular ideas in science fiction. Tunnels in space-time connecting remote points. You enter in one place and come out in another, bypassing enormous distances. Hypothetical shortcuts through curved space. It sounds fantastic, but the mathematics of general relativity allows such structures. The first solution to Einstein's equations describing a wormhole was found by Schwarzschild himself. More precisely, the solution was later extended by Albert Einstein and Nathan Rosen in 1935. They showed that the Schwarzschild metric can be interpreted as a bridge between two asymptotically flat spacetimes. Two different worlds connected through the throat of a black hole. The problem is that the Einstein-Rosen bridge is unstable. It exists only for a moment, then collapses. Nothing can pass through it faster than it collapses. Therefore, in classical general relativity, such wormholes are non-traversable. They connect two worlds, but one cannot travel from one to the other. But Einstein-Cartan theory changes the situation. The torsion of space-time stabilizes the throat. Instead of an instantaneous collapse, a wormhole can exist indefinitely. And moreover, inside it, there can be space where matter does not fall into a singularity, but expands, creating an entire universe. Poplawski shows mathematically how this works. When matter falls into a black hole, it passes through the event horizon and enters the throat of the wormhole. But instead of collapsing into a point, the throat expands from within thanks to the quantum bounce, and this expansion creates a new space-time, the internal universe of the black hole. On one side of the wormhole is the parent universe where the black hole is located. On the other side is a white hole. A white hole is the reverse side of a black one, a region of space-time that cannot be entered from the outside, but from which one can emerge. A mirror image of a black hole. For the inhabitants of the inner universe, a white hole looks like the Big Bang, a source of matter and energy from which everything appeared. They cannot penetrate back past the horizon of the white hole into the throat, just as we cannot return in time to before the Big Bang. This is a one-way boundary, but in the opposite direction. So the structure turns out like this. A black hole in the parent universe, the throat of a wormhole, the internal universe, and a white hole on the opposite side. A bridge between worlds, but a non-traversable one. Matter can enter through the black hole but cannot leave. Information can appear from the white hole but cannot return back. And if our universe is inside such a structure, then the Big Bang is that white hole, the moment when matter that fell into the black hole of the parent universe bounced and began to expand, creating us. And the cosmological horizon we observe at the edge of the visible world is the event horizon of that very black hole, if viewed from the inside. A striking structure. Two worlds separated by impenetrable horizons. Between them is a tunnel in space-time inside which is an entire universe. We live not just inside a black hole. We live inside a wormhole connecting the parent world with what lies on the other side of the white hole. And what is there on the other side, we do not know. Perhaps another universe, perhaps a void, perhaps something completely unimaginable. A white hole is an exit from our universe, but an exit into the unknown. And we cannot get there because the white hole is in our past, at the moment of the Big Bang. Time flows only forward, so returning to the white hole is impossible. But every black hole we observe in our universe can be the same structure. It can contain its own internal universe, its own wormhole, its own white hole. And in those universes, black holes can also form, containing their own universes. Infinite nesting, a cosmic matryoshka going as deep as the laws of physics allow. Poplawski's theory turns black holes from points of no return into portals of creation. Each hole is the seed of a new universe, and each universe is a garden in which new seeds grow. An eternal cycle of birth and death, creation and destruction, closed in itself and infinite. And we are part of this structure, one of the levels of the hierarchy. We are not at the top, not at the base, but somewhere in the middle. Above us is the parent universe, possibly with its own parent and so on up. Below us are daughter universes inside the black holes we observe, and their daughters, and so on down. A ladder of worlds that we cannot climb or descend, but can know exists. And this gives rise to a dizzying question. How many levels are in this hierarchy? If Poplawski's model is correct, if every black hole indeed contains an entire universe, and every universe gives birth to many black holes, then the structure of the cosmos turns out to be infinitely complex. Not just one universe, not just a multiverse with parallel worlds, but a hierarchical multiverse organized on the principle of nesting through black holes. Imagine, somewhere in a huge parent universe, a star collapses and a black hole forms. For observers in that universe, this is just an astronomical event, one of billions. A star died, leaving behind a dark object of a certain mass and size. They can study this black hole, measure its mass, rotation, observe how it attracts surrounding matter. But they do not know that inside this black hole, an entire history is unfolding. Matter that fell behind the horizon reached Planck density, bounced, and began to expand. A new universe was born, ours. The first particles appeared, the first atoms, the first stars. Galaxies and planets formed. Life arose and civilization appeared. Billions of years of evolution, trillions of events in an uncountable history. Interestingly, for an external observer, this internal universe exists in a frozen moment. He sees the black hole, matter falling toward the horizon, but never crossing it. From his point of view, the entire history of the internal universe, from the Big Bang to a possible end, happens in an infinitely small interval of time on the horizon itself. This is the paradox of relativity. For us inside, billions of years have passed. We observe evolution, changes, history. But from the outside, all this is frozen in one moment, sealed inside the event horizon. Both perspectives are equally real. They simply describe one geometry of space-time from different sides. And exactly the same way in our universe stars collapse and black holes form. We observe them as astronomical objects, measure their masses, build models, study accretion disks around them. But we do not know that inside each such hole there may exist its own universe with its own galaxies, its own stars, possibly its own life and civilizations. These civilizations will never know about us. We will never know about them. The event horizon is absolute. Information does not pass in either direction. We are forever separated by an impenetrable barrier of space-time. But mathematics connects us. The structure of the cosmos is one. The same laws of physics work at all levels. Einstein's theory, quantum mechanics, thermodynamics. All this is universal. And if these laws allow for an infinite hierarchy of universes through black holes, then it exists. How many levels? Infinitely many in both directions. Upward to increasingly massive and slowly evolving parent universes. Downward to increasingly small and fast-living daughter worlds. A ladder without beginning or end. Each level has its own scale of time. In the parent universe containing the black hole inside which we are, time flows slower. Perhaps our 14 billion years are a second for them. And in the daughter universes inside the black holes in our universe, time flows faster. Perhaps the entire history of such a universe from birth to death passes in the time it takes us to blink. A hierarchy of scales. Each level lives at its own pace, exists in its own space, evolves according to its own laws, but all are connected through black holes, portals between worlds, non-traversable yet real. And the philosophical question arises, is there a bottom to this hierarchy or a top? Classical physics says there is a minimum scale. Planck length, Planck time. Nothing smaller than this exists. Space-time is quantized. But Einstein-Cartan theory allows that even on Planck scales, structures can exist. Tiny black holes containing micro-universes. And at the top, is there a limit to how large a universe can be? We do not know yet. Perhaps the hierarchy goes up infinitely. Perhaps somewhere there is an ultimate universe, the largest one that contains all the others. Or perhaps the structure is closed on itself. The top level connects with the bottom through some cosmic loop, and the hierarchy forms a cycle. We cannot answer these questions with observations because we are locked at our level. All we can do is build theories, make mathematical deductions, check indirect consequences, and try to understand our place in this dizzying structure of the cosmos. But one thing is clear. If the theory is true, we are not alone. Not in the sense of life in space. That is another question. We are not alone in the sense of worlds. There exists an infinite multitude of universes nested into each other, connected through black holes, and each of them is a separate reality with its own history, its own laws, and its own fate. And we are one of the levels of this cosmic matryoshka. Time is the strangest of all coordinates. We cannot move back in it, only forward. We cannot speed it up or slow it down by our own will. It flows, and we flow with it. No general relativity shows that time is not absolute. It depends on gravity, on the speed of movement, on the curvature of space-time. And for different observers, it flows differently. The classic example is the twin paradox. One twin remains on Earth, the other flies on a relativistic ship to a distant star and returns. For the traveler, a year passes. For the one remaining on Earth, 10 years. They meet, and one is 9 years younger than the other. Not an illusion, not a deception of perception, a real difference in the time passed. The same thing happens in a gravitational field. The stronger the gravity, the slower time flows. On the surface of a neutron star, a second stretches. In the vicinity of a black hole, time slows down even more, and on the event horizon, it stops completely from the point of view of an external observer. But for someone crossing the horizon, time continues to flow normally. He does not notice anything special. And here an interesting paradox begins. If we are inside a black hole, our time and the time of an external observer are connected in a strange way. From the point of view of the parent universe, our entire history from the Big Bang to the possible end happens in one frozen moment on the event horizon. But from our point of view, billions of years pass, evolution unfolds, and the cosmos changes. Both perspectives are equally real. They simply describe one geometry from different sides. Now think about the consequences. If a black hole forms in our universe, a new universe can be born inside it, which for us will exist in a frozen moment, but for its inhabitants, aeons will pass. This means that every black hole we see already contains the full history of an entire universe from beginning to end. The entire cycle of existence, or all cycles if the universe pulsates. All this is enclosed inside the event horizon, hidden from us, but already realized in its own time. And the reverse is also true. For the parent universe containing the black hole inside which we are, our future is already determined. Not in the sense of predetermination. We have free will, quantum uncertainty, everything as usual. But in the sense of time, our entire future already exists from the point of view of an external observer. He sees the black hole as a frozen object inside which the entire history of the universe, from the Big Bang to the end of time, has already occurred. A dizzying thought. We live, think, act, choose. For us, Time flows, the future is open, and history is not yet written. But for someone outside, our entire history is already in the past. A frozen picture sealed behind the event horizon. This is not determinism in the usual sense. No one determines our future in advance. We ourselves create it with our actions and decisions. It is just that from different points of view in space-time, this future looks different. For us, as an open possibility, for an external observer, as an already realized history. And this concerns not only us. Each universe in the hierarchy lives in its own time. For the universe one level above, time flows slower. For the universe one level below, faster. Each level exists at its own pace, but all are connected by one geometry of space-time. One can imagine it as concentric circles on water. Each circle is a level of the hierarchy. The outer circles expand slowly, the inner ones quickly, but they are all part of one splash, one event in four-dimensional space-time. Different paces, but a single structure. So time inside and outside a black hole is not two different times. It is one time seen from different perspectives, and both perspectives are real. Both describe what is, just on different sides of the event horizon. Imagine that tomorrow morning you wake up and find out that everything you knew about the universe requires rethinking. Not in details, but fundamentally. The universe is not a boundless cosmos expanding from a point of the Big Bang. Possibly, it is the interior of a black hole limited by an event horizon. What will change? At first glance, nothing. The sun will rise as usual. The stars will shine, galaxies will scatter, the laws of physics will work. Your life, your plans, your dreams, everything will remain the same because locally, here and now, the geometry of space-time is the same. But the understanding will change. Your place in the cosmos, the meaning of what you see in the night sky. Beyond the cosmological horizon is possibly not a continuation of our universe, but another world. A parent universe containing a black hole with us inside. A region of reality with which we cannot exchange information under any circumstances. This changes the representation of our future. Space travel is possible to the stars, to other galaxies throughout our space-time, but to go beyond its limits, to cross the horizon in the reverse direction, is physically impossible. Our universe is a closed system. But there is another side. If every black hole in our universe contains its own universe, then the potential for the existence of life and intelligence is enormous, not only on planets around stars in our world, but also inside every black hole, of which there are billions. Inside each is an entire universe with its own galaxies, stars, possibly planets, life, and civilizations. We cannot contact them, but we can know they are there, and this changes the perspective of loneliness. We are not alone in the cosmos. It is just that other intelligences, other civilizations, can exist not only on other planets of our universe, but also at other levels of the hierarchy. In the parent universe, in daughter universes, in the daughters of our daughter universes. An infinite multitude of worlds, each with its own history, each with its own inhabitants. All are separated, all are isolated, yet all are part of a single structure of the cosmos. A cosmic family whose members will never meet but know of each other's existence through mathematics and theory. And also, this changes the meaning of the Big Bang. Earlier, it was an absolute beginning. Before it, nothing. Time began with it. To ask the question, what was before the Big Bang, was considered meaningless. Now, there is an answer. Before the Big Bang was the parent universe. Matter in it collapsed into a black hole, reached Planck density, and bounced. And this bounce is our Big Bang. This means the universe did not arise from nothing. It arose from something, from the matter and energy of another world. And when our universe ends its cycle, when it collapses back or reaches thermal equilibrium, It will not be the end of everything. It will be the end of one level in an infinite hierarchy. What does this mean for us personally, for our lives, our values, our goals? Perhaps nothing. We still live here, in this universe, on this planet. At this time, our actions have consequences here, not in the parent universe or daughter worlds. We cannot influence other levels of the hierarchy, and they cannot influence us. No knowledge changes perception. The realization that you are part of an infinite structure, that your world is one of many, that reality is much larger and stranger than it seems. This gives perspective. Humility before the scale of the cosmos, and at the same time, pride that we are capable of understanding this, capable of building a theory describing such a dizzying structure. We, tiny creatures on a tiny planet in a small galaxy, in one of the countless universes, were able to think our way to this. We're able to see that our world is not all that there is, that beyond the horizon lies something greater. And although we cannot get there, we can know about it, and that is already a lot. Of course, Poplawski's theory is not a proven fact. It is a hypothesis, although a mathematically grounded one. It has problems and questions that still require answers. And before we accept it as truth, we need to analyze what exactly causes doubt, where the weak points are, what does not fit, and what requires additional confirmation. The first problem is experimental verification. Science requires that theories make predictions that can be checked. If a theory is unverifiable, it goes beyond the framework of science and becomes philosophy or speculation. And with this, the theory of a universe inside a black hole faces difficulties. The main prediction is the rotation of the universe. Telescope data showed an asymmetry in the distribution of galaxy rotations, which is consistent with the theory. But one observation is not enough. Additional confirmations from independent sources are needed. Traces of rotation must be sought in other aspects of the large-scale structure, in the cosmic microwave background, in the distribution of galaxy clusters, and in the anisotropy of cosmic rays. And this is where the problems begin. The analysis of the cosmic microwave background conducted by the Planck satellite did not show significant anisotropy that would indicate a rotation of the universe. There are small deviations from isotropy, but they are explained by the movement of our galaxy and local structures. Global rotation is not visible. Perhaps the effect is too weak to be detected with current precision. Perhaps it manifests only on certain scales that we have not yet explored sufficiently. But for now, the absence of a clear signal in the cosmic microwave background is a problem for the theory. The second problem is the alternative explanation of observations. The asymmetry in galaxy rotation discovered by Webb may have other causes. It might be the effect of our own movement in space, which creates the illusion of a preferred direction. It might be a feature of galaxy formation in the early universe related to processes we do not yet understand. Astronomers are checking these alternatives, trying to account for all known effects and correct the data for the movement of the Earth, the Sun, and the galaxy, but the statistics are not yet strong enough to definitively exclude alternative explanations. More data, more galaxies, and more precision are needed. The third problem is theoretical. The Einstein-Cartan theory, on which Poplawski's model is based, is not generally accepted. It is an extension of general relativity that adds space-time torsion. Mathematically, the theory is not contradictory, but it has little experimental confirmation. Torsion effects manifest only at extreme densities unreachable in laboratory conditions. Therefore, it is impossible to verify the theory directly. Some physicists believe that torsion is an unnecessary complication, that classical general relativity works perfectly and there is no reason to expand it. Others believe that torsion must exist because matter has spin, and spin must affect the geometry of space-time. The debate continues, and there is no consensus yet. The fourth problem is energetic. If every black hole contains an entire universe, where does the energy for this universe come from? Inside a black hole, there must be a huge mass of energy sufficient to create billions of galaxies. But from the outside, we see a black hole of a certain mass, say 10 solar masses. How can a universe with a mass of trillions of suns fit inside it? The answer is related to how gravitational energy works. In general relativity, gravitational energy can be negative. When matter falls into a black hole, it loses energy by emitting gravitational waves. This energy leaves, and the remaining mass becomes part of the black hole. Inside the black hole, this mass can expand, creating space, because gravitational energy compensates for the positive energy of matter. This is a complex idea, and not all physicists agree with it. Some believe that the energy balance does not add up, that additional energy sources are needed, which the theory does not yet explain. Others say that everything is fine, that the mathematics is correct, and it is simply our intuition that fails us. The fifth problem is observational. If our universe is inside a black hole, there should be some traces of this in the observed data. Besides rotation, there should be other effects, such as a specific distribution of matter, features in cosmological parameters, or anomalies in expansion. And here, standard cosmology works surprisingly well. The lambda cold dark matter model, describing the universe as expanding from a singularity with dark matter and dark energy, explains almost all observations with high precision. Yes, there are unresolved questions: the nature of dark matter, the nature of dark energy, the horizon problem, the flatness problem. But overall, the model works. Poplawski's theory must explain the same observations but from different positions, and it is not yet clear whether it does this better than the standard model. Perhaps it explains some anomalies that the standard model does not, but for now, these anomalies are not strong enough to refute standard cosmology. So the theory of a universe inside a black hole has problems, serious ones requiring solutions. But this does not mean the theory is incorrect. It means it is in a stage of development, that additional research, more accurate data, and a deeper understanding of physics are needed. And if these problems can be solved, the theory could become a new paradigm of cosmology. If not, it will remain an interesting mathematical model showing what strange possibilities general relativity allows. The question is how to verify what is by definition inaccessible to direct observation. We cannot look beyond the event horizon of the black hole we are in. We cannot send a probe into the parent universe and return data. We cannot look inside the black holes in our universe and see if there are other worlds there. So how can the hypothesis be verified? The answer is through indirect consequences. If the theory is correct, it must make predictions about observable quantities, the distribution of galaxies, the properties of the cosmic microwave background, and the nature of the expansion of the universe. And these predictions can be verified. First, the rotation of the universe. We have already discussed this. If the universe was born inside a rotating black hole, there must be a preferred axis of rotation. Webb data showed an asymmetry in the rotation of galaxies. The next step is to expand the sample, study more galaxies at different distances in different parts of the sky. Build a three-dimensional map of the distribution of rotations. If a preferred axis truly exists, it will manifest in these data. Second, anisotropy of the cosmic microwave background. If space rotates, it should create a specific pattern in the temperature fluctuations of the background, not just random oscillations, but an organized structure related to the axis of rotation. The Planck satellite did not find such a pattern, but its sensitivity might have been insufficient. New missions, more sensitive detectors, and better analysis methods could detect the signal. Third, gravitational waves. If the universe pulsates, expanding and contracting in cycles, it should create a background spectrum of gravitational waves, not from specific events like black hole mergers, but from the overall dynamics of space-time. Detectors could discover such a background if it is strong enough. Fourth, the distribution of black holes. If every black hole contains a universe, this affects their evolution. An internal universe adds mass to the black hole or, conversely, decreases it. How does this affect the observed mass distribution of black holes? If the theory predicts a specific distribution different from standard models, this can be verified by observations. Fifth, quantum effects at the event horizon. The theory suggests that the event horizon of a black hole is not just a geometric surface, but a place where quantum processes occur. Hawking radiation, the information paradox, quantum fluctuations. If the universe is inside a black hole, these processes could leave traces in cosmological data, perhaps specific features in the distribution of dark matter or dark energy. All these verifications require time, resources, and new technologies, but they are possible. And if even a few of them give a positive result consistent with the theory, it will be a strong argument in its favor. And there is another approach, philosophical but important. If the theory explains mysteries that standard cosmology cannot explain, that is also an argument. For example, the fine-tuning problem. Why are the constants of nature exactly as they are? Why the mass of the electron, the charge of the proton, the speed of light, the gravitational constant? All these numbers are selected such that complex chemistry, stars, planets, and life are possible. The standard answer is the anthropic principle. If the constants were different, we would not be here to ask the question. But that is not an explanation. It is a statement of fact. Poplawski's theory suggests a mechanism. If universes reproduce through black holes and each new universe inherits the constants of the parent with small variations, then over time, evolution will lead to the survival of universes with constants favorable for the formation of black holes. And black holes form in those universes where stars are possible, and stars are possible where constants allow complex chemistry. Cosmic evolution, an analog of biological evolution, not the natural selection of living beings, but the natural selection of universes. Those that produce more black holes survive and multiply, and those are the ones where constants are tuned for star formation. And we are in one of such universes not by chance, but because it is the product of a long chain of cosmic evolution. It is a beautiful idea, but it is impossible to verify it directly. We cannot observe other universes or compare their constants with ours. All we can do is evaluate the internal consistency of the theory, its elegance, and its ability to explain what otherwise remains a mystery. And here, Poplawski's theory has an advantage. It unites cosmology, black hole physics, and quantum gravity into a single framework. It gives a mechanism for the birth of the universe that does not require a beginning from nothing. It explains why the universe expands, why there is a cosmological horizon, and why the constants are tuned as they are. And all this follows from one idea. Universes are born inside black holes. Verifying this idea is difficult, but possible. And if the verifications give a positive result, we will witness a revolution in our understanding of reality, no less than the discovery that the Earth revolves around the Sun, or that the universe is expanding, or that time is relative. We will learn that we do not live in a boundless cosmos, but inside a limited region of space-time, that our world is one of countless worlds nested into each other, that beyond the horizon lies something greater, strange, and unfathomable, and that we, despite all our smallness, are capable of understanding this, and that is already a victory of reason over ignorance. Imagine that 100 years have passed. Physicists have verified all the predictions of Poplawski's theory. They have accumulated enough data to confirm, yes, we live inside a black hole. This is not a hypothesis, but a proven fact. Textbooks have been rewritten, cosmology has been revised, and our representation of the cosmos has changed forever. What does this mean for humanity, for our culture, our worldview, our place in existence? Perhaps it will be similar to the Copernican revolution. When Copernicus showed that the Earth is not the center of the universe, but one of the planets revolving around the sun, it destroyed the anthropocentric picture of the world. Man ceased to be the center of creation. We found ourselves on the outskirts in one of many solar systems. Then Galileo and Newton showed that the heavens obey the same laws as the Earth. There is no division into sublunary and supralunary worlds. Everything is one. Then Darwin showed that we are not a special creation, but a product of evolution, relatives of all living beings on the planet. Then Hubble showed that our galaxy is one of billions. Each time, humanity lost a part of its specialness. It turned out that we are not at the center, not unique, and not separated from the rest of the world. And each time it was painful, but liberating. We lost illusions, but gained the truth. We became humbler, but wiser. The discovery that we are inside a black hole will be the next step. We will lose the illusion that our universe is all there is. We will learn that we are trapped, that beyond the horizon something greater and unreachable exists, that we are one of the levels in an infinite hierarchy, not special, not unique. But we will gain understanding. We will learn where we came from, understand the structure of the cosmos, and see our place not in a void, but in a grandiose cosmic architecture. And this will give us a perspective we did not have before. Perhaps it will change our philosophy. Questions about the meaning of existence, the purpose of life, and the place of man in the cosmos will all receive a new context. If we are inside a black hole, if our world is one of many, if our entire history is a moment in the eyes of an external observer, then what does this mean for our values? Some will say, it means nothing. We still live here, in this reality. Our actions have consequences for us and for those nearby. It doesn't matter that there are other worlds outside. What matters is what happens here and now. Others will say, it changes everything. The realization of the infinity of the structure, one's own smallness in it, and the futility of attempts to break out could lead to nihilism, to despair, to a sense of being lost. But there may be a third way. The understanding that we are part of something larger, that our world is connected with other worlds even if we cannot see them, can give a sense of unity, not loneliness, but belonging. We are not random creatures in a void. We are part of a cosmic hierarchy, the product of a process that reproduces universes through black holes. We have a place in the structure of the cosmos, and although we cannot go beyond its limits, we can know about it. And knowledge is already a lot. Perhaps this will inspire us to explore deeper. Not space, we already explore that, but the very nature of reality. Quantum gravity, the structure of space-time, the possibility of other dimensions. If we are inside a black hole, what else does reality hide? What other secrets await discovery? And perhaps this will unite us. The realization that we all, residents of one universe, one space-time, beyond which stretches something unfathomable, can erase the boundaries between nations, cultures, and ideologies. We are all in the same boat, or rather, in the same black hole, and this makes our disagreements less significant against the backdrop of the grandiosity of the cosmos. But these are all speculations. Reality will show how humanity will react if the theory is confirmed. Perhaps there will be a revolution in thinking, or perhaps most will simply shrug their shoulders and continue to live as they lived. After all, the discovery that the Earth revolves around the sun did not change the daily lives of people. The sun still rose in the east and set in the west, but it changed how we think about ourselves and the world. So if we truly live inside a black hole, it is not the end, but the beginning. The beginning of new understanding, new questions, and new research. We learned that our world is stranger than we thought, that reality is deeper than it seems, and that beyond the visible horizon hides infinity. And now our task is to live with this knowledge, to use it to become wiser, humbler, and more curious, to continue exploring, asking questions, and seeking answers. Because even if we are limited by the boundaries of our universe, our mind is free. We can think about what is beyond, build theories, make predictions, and verify hypotheses. And in this lies our uniqueness, not in where we are, but in the fact that we are capable of understanding where we are. So we have traveled a long way from the Schwarzschild formula, written in the trenches of the First World War, to the data from the James Webb Telescope, peering into the infancy of the universe. From the Pathria good hypothesis, expressed half a century ago, to Poplawski's theory suggesting a concrete mechanism for the birth of universes inside black holes. From observing the strange coincidence of radii to the realization that this may not be a coincidence, but a fundamental property of our reality. We have learned that our universe may not be a boundless cosmos, but the interior of a giant black hole. That the cosmological horizon we consider the boundary of the observable world may actually be an event horizon beyond which lies another universe. That the expansion we observe and call the consequence of the Big Bang may be a quantum bounce of matter from the Planck density inside a black hole. We have understood that black holes are not points of no return, but portals of creation. That each hole can contain an entire universe with its own galaxies, stars, and planets. That the structure of the cosmos may be an infinitely nested hierarchy where universes are born inside black holes, which themselves are in other universes. We have realized that time inside and outside a black hole flows differently, that our billions of years may be a moment for an external observer, and that the future of our universe, from his point of view, already exists, enclosed behind the event horizon. And we have seen that despite all the strangeness of this picture, it is mathematically correct, physically possible, and possibly confirmed by observations. The asymmetry in galaxy rotation discovered by the Webb telescope may be the first real evidence that we live inside a cosmic trap. But whatever future research shows, the mere possibility of such a theory already changes our perspective. We are used to thinking of the universe as something absolute, final, and all-encompassing. Now we know. Perhaps it is not so. Perhaps our world is only one of the levels in a grand structure that stretches up and down into infinity. If you are interested in following the development of this story, subscribe to the channel and give it a like. Ahead of us lie new telescope discoveries, new data on the large-scale structure of the universe, and new verifications of Poplawski's theory. And perhaps very soon we will learn the final answer to the question that until recently seemed like pure fiction. Do we live inside a black hole? For now, we can only look at the night sky and think, what is there beyond the horizon? What world hides on the other side of the invisible boundary? And realize that even if we never know the answer for sure, the very ability to ask such questions makes us amazing creatures. We, the tiny inhabitants of a small planet, possibly trapped in a cosmic snare, were able to think our way to this. We're able to build a theory describing the structure of the cosmos. We're able to see beyond the obvious, and that is already a lot. This is perhaps the most important thing that distinguishes us from everything else in the universe, or in the universes, if there are many of them. The ability to understand, the ability to wonder, the ability to seek the truth, even if it overturns everything we knew. Thank you for being with me on this journey to the edge of reality and beyond. Until next time.